Right. So this is basically a geometrical thing that we use to find the radius of curvature. So let's say this is your capillary. So I'm drawing a very sort of magnified version of it, but it's a thin capillary. So this is the top part of the capillary. It's extending like this into the liquid. Okay, now, next is we will draw the liquid surface. So here, let's say the liquid surface is just something like this, more or less a flat surface. But as it comes here, thoda sa it again, rises up like this, and here it rises up like this. But more importantly, inside the capillary, what does the liquid surface look like? It looks like this, but this is the ring of contact. The actual surface is like a bowl. This is like the actual surface.
Okay.
You have to imagine this is like a three-dimensional surface. So this is the liquid. Okay. Now what is happening? The standard thing that you know over here is the radius of the capillary itself. That is this one. If this is the symmetry line, then you know the radius of the capillary. This one is your, let's say, capital R, which is given in the question to us as whatever. But what is happening? Ye jo surface, this curved one, we have to find the radius of that meniscus. Okay? So what we do is at the point of contact, we draw a tangent. Okay. And at this point of contact, we draw another tangent. So that is the surface of contact, right? So the contact angle is nothing but this angle, theta. Yeah, that is what we define as contact angle. Now, in this case of water and this thing, it is equal to 0. But in a general case, it can be any acute angle. So these are the two tangents. Now you drop two normals from here.
Sir,
so wherever the normals intersect, जब भी angle of
contact 0 रहेगा तभी radius of meniscus 0 sorry infinite रहेगा ना?
When the angle of contact is 90 degrees, then the radius of meniscus will turn to infinity. Okay, I'll explain why. You'll understand in a moment. Okay, so now see what is happening. ये जो C है, that is the center of curvature of what? It is the center of curvature of the meniscus.
Okay.
Okay. So let us consider the meniscus has a radius. Let us consider the radius of the meniscus is small r. So in this diagram, this is the center of curvature and this is the surface of the meniscus. Now, so this one is small r.
Okay.
Correct?
Yes.
So I'm zooming into this diagram again. So see now this one is small r, whereas if you drop a perpendicular here, this one is capital R, and this angle is theta. So this is 90 minus theta. So this angle is theta. So now concentrate on this right angle triangle. So this is small r, this is capital R, and this angle here is theta. So you can see what is the relationship between them. Small r by capital R, capital R by small r is cos theta. Okay. So that is why you will get that relation, that small r is in fact capital R by cos theta, which is why when theta is tending to 90 degrees, this is becoming a flat surface. So that time the radius of the meniscus is tending to infinity.
Okay, yes.
Whereas when theta is 0, this is a hemisphere.
Yes, yes.
So those are the special cases. So in fact, you can over here even note them as two special cases. Okay. So for theta tending to 0, like glass and water, okay, what happens is that the meniscus becomes a hemisphere. It's a hemisphere. And because it's a hemisphere, then R tends to become equal to capital R. Whereas the other extreme case is that theta equal to 90 degrees. That is when actually what will happen, your meniscus will look flat like this, because the contact angle is 90. So because it's flat, it doesn't have a radius of curvature. I mean, it's a plane surface, so its radius is tending to infinity. So those are like the two extreme cases. Okay, so this is an important type of question, and hope this is clear. So I'll just leave you with a moment with this diagram, okay, with the magnified version of the diagram. Then I'll switch off my screen share so that I can get more questions from you guys. So hope this is clear, people.
Sir, can we just zoom out because I want to take a screenshot of the answer.
Yeah. So you want me to magnify it or make it smaller?
Make it smaller.
Make it. You want me to zoom out? Okay, cool. I'll do that. Yes, I'm doing that. Tell me if it's okay. Is this fine for you?
No, sir, 25%, 50%.
Acha, 50% कर दूँ. Okay.
Okay.
Okay. Is this clear? Okay.
Yes.
Okay.
So can you show the previous one, previous answer?
Which one? The rolling object, that one?
Yes, yes.
Yeah, I'll send that. In fact, you know what? I will send you the screen. I will send you the whiteboard. Okay.
Okay.
I will do this entire whiteboard of today's problems. Okay. So don't worry about that. But I'm doing this at the moment. Okay. In this. But next question onwards, don't worry. I'll send you the whiteboard. And I'll also send you a recording of the session. Okay. Only I did not record the first question. I forgot at that time. Second question I have.
Okay.
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 Okay. So we
Sir,
are going to go.
can you just pull it down?
Yeah.
Okay.
Pulling it down. This is the next part. Right?
Yes, sir. Okay. Thank you.
Okay, good. So I am stopping and share anything else you have.
Hello.
Yeah. Srinidya, you have
Sir, 1 second. I'm
something to share? Yeah.
1 second.
So I see Prayush is also here, and I think Prayush had one worksheet from last time which I could not get to, that question of magnetism. So I'll be coming to that later. Okay. So in this, we are doing question number 14. Is it this one? Right.
And this B
Let's
part.
go through the question.
B part.
Oh, that theta equal to 0, that part.
Yeah. And with constant pitch. I'm not getting that.
Okay. So let me understand this. Consider, okay, if you can you just, yeah, right. Consider the motion of a positive point charge in a region where there are simultaneous electric and magnetic fields, okay, which are uniform. And you can see that the electric and magnetic fields are what type? They are parallel, right? They are both along J cap.
Yes.
So at a certain time, the charge has a velocity v in the xy plane, okay, making an angle theta with the x-axis. Which of the following options is or are correct? So if theta equal to 0, the charge moves in circular path, blah, blah. Okay. So see what is happening. You have an electric field along the y-axis. So
yes.
that will always create a uniform force along the y-axis. So the particle will have a uniform acceleration along the y-axis. There's nothing, okay. Can the magnetic force be along the y-axis? No, because your magnetic field is also along the y-axis. So that means there is nothing to cancel your electric force. Are you understanding the point, people?
Yes.
So this, so that means मेरा क्या हो रहा है? Acceleration का y component वो constant रहेगा. That will be how much? It will be equal to q into e divided by m. Q into m naught, q into e naught divided by mass, right? Whereas the magnetic field is along the y-axis. So if I give it any initial velocity, in which plane? In the plane perpendicular to that one. That means the xz plane.
Yeah.
Then it will go into a uniform circular motion. Correct. So in general, what type of path is possible? One is that if you release the particle from rest, it will just go in 1D motion because of the electric force. There won't be any magnetic force.
But
because
it
velocity created
due to magnetic.
because देखो ना अगर velocity उसका सिर्फ y axis के along है, then magnetic force will be 0 ना. V cross B will be 0.
Yes.
Right. So if you release the particle from rest, for example, it will just have uniform acceleration along the y axis, but magnetic force will never act on it because there is no velocity along in the xz plane. So it will be a uniformly accelerated 1D motion. Okay. Next, now suppose you give it an initial velocity in the xz plane, anywhere in the xz plane. So what is the magnetic field doing on it? It's going to create uniform circular motion. QVB is equal to mv square by r, that thing.
Yes.
So in the xz plane, there will be uniform circular motion, but along with that, along the y-axis, there will be what? There will be uniformly
Linear.
accelerated motion. So what type of motion it will be? Yeah, linear
Helical.
acceleration. So it will be a helical path, but with a constantly increasing pitch. No, it's not like the helical path you have in uniform magnetic field, because वहाँ पे क्या हो रहा है? Axis के along acceleration नहीं होता है. Axis के along the parallel component of velocity is constant. But here the parallel component of velocity, which is along the y-axis, that will keep increasing with time.
Okay.
It looks like a helix, which you're kind of you're constantly
With
changing its shape.
we are increasing the pitch.
वो deform होता जा रहा है. Like if you take a spring and progressively for the circles of the spring you keep separating them more and more. So how it will look? It will look like a deformed kind of spring. The radius constant है, but the pitch is increasing. So that kind of path will happen. Okay. Yeah. So so will you be able to solve the question based on this?
Yes.
Okay, good. Right. So no problem, Dhruv. It's okay. So who's going to be next for doubts now? Does Trinithia, you have some? Okay, Prayush. Good. Yeah, Prayush, this question. Can you just magnify it a little bit for everyone to see?
Sir,
Yes.
have you discussed the doubts I had sent?
Yeah. This one was one of the questions. Okay. This is Prayush, right? Yeah.
Yes, sir. Sir,
Yeah, wait.
no, I didn't speak the last sentence. Yeah.
Yeah, just a moment. Prayush, do one thing. Stop the share. I have this question on my desktop, so I'll share it with you.
Okay, sir.
Yeah. Okay. So I should be able to share it. Just hang on. Okay. Yeah. It should be coming up.
Yes.
No. Yeah. So are you people able to see the question properly?
Yes, sir.
Okay. So now you can see it clearly. Okay.
So you can just yes, sir.
It's all clear now.
Yes, sir.
Okay. Yeah, I'll come to the individual parts, but just the paragraph. So I'll explain the paragraph first. So all of you just go through this question. It's quite an interesting problem to do with induction. So I'll explain how it works here. So just go through the language of the paragraph, then I'll explain in detail. Okay, right. So have you got a chance to read through it, all of you?
So just 1 minute.
Yeah, just take your time. Go through it.
So it's confusing.
Okay, done. Okay, fine. So even if you got a gist of it, fine. I'm explaining the question in detail. Okay, so now coming back to my whiteboard. So first of all, let me explain the geometry of the question over here. Okay. So what is happening is, forget about spaceship and all that. You can treat it like an everyday situation also. You have a metallic disc. The spaceship is basically shaped like a disc. So we can just do it as a problem of a metallic disc. So you have a metallic disc which is falling vertically downwards near the Earth's surface. Let's say. It's a different planet, but let's say it's near the Earth's surface, such that the diameter of the disc is along the vertical. So the geometry is such that the disc is lying in a vertical plane. The disc is not lying in a horizontal plane. So as it is falling, one of its diameters will be vertical, one of its diameters will be horizontal, but the plane of the disc is in the vertical plane.
Okay.
And while there is gravity acting vertically downwards, there is also a horizontal magnetic field, just like the BH of the Earth, the horizontal component of the Earth's magnetic field. So on that planet, we are assuming there's only BH, there's no BV, there's no vertical component of the magnetic field of the planet. So first, let's try and make a sort of three-dimensional diagram to understand this. Okay. So if this is the disk seen from one side. So imagine it's something like this now. So I'm really going to struggle with this drawing, but just bear with me. Okay. So it's got a very small thickness, right? Got a very small thickness. So that thickness is negligible, but its radius is r. Now the point of axis. So this disk is lying in which kind of plane? It's lying in a vertical plane. So if I take my coordinate frame like this, that this is, let's say, the disk is lying in this vertical frame, let's say. So in my diagram now, what is happening is, if I have taken this as X, Y, and Z, my Y axis is the vertical. Okay. So gravity will be pointing like this. So we can write gravity as a vector as minus G, J. But also in this region, there is a magnetic field, which is horizontal. And let's assume that, I mean, according to what is given in the question, let's imagine the magnetic field lines, which are like this. So these are my magnetic field lines.
Sir, can you write it in the vector form?
Yeah. So magnetic field directly we can write it like this. So the magnetic field B, which I've shown here like this, which are these kind of lines, they are nothing but, let's say, some constant into K cap. So this is the two types of fields there are. Okay. Now in this we have to understand the metallic plate which has radius R and it also has thickness D, where D is small compared to R. That's also given to us. How its dynamics will look like. So now what I'm going to do first is I'm going to draw the diagram from the point of view that I'm looking into the Z axis. Okay, so I'm looking into the XY plane. Down the Z axis, if I'm looking, like I'm seeing straight into the XY plane. So if I now redraw my diagram such that I'm looking straight into my XY plane and the Z axis is coming out of the plane in this diagram. So my magnetic field will be coming out of the plane. There's a uniform magnetic field B naught K cap coming out. So in this case, I will, the diagram of the disk, I'll be seeing it from the side. No? So it will look like this. I'll see this is the thickness of the disk. And this is the diameter, so 2R. Be like this. Whereas actually it's a disk. So this is the disk in the YZ plane. Like this. Okay. So far everything is clear, people? Okay, now let us understand the state of motion of the disk. So if the disk has a downward velocity v at this point of time and a downward acceleration e, so what are the forces acting on it? Let's understand that. So first of all, there is gravitational force, which is acting through its center of mass, mg, like this. Okay. So I have the gravitational force mg, which is acting through the center of mass, which is giving it a velocity v downwards. So at some time, if there's an instantaneous velocity v downwards, what is happening? Your concept of magnetism will tell you that any free electron inside the disk, it is going to experience what kind of magnetic force. See, v is pointing downwards, so v cross b is pointing in which direction? Towards the right. V cross b is pointing along plus I cap because velocity is downward and v is coming out of the plane. So the electron will experience a magnetic force like this, okay, which is EVB in magnitude. Okay, so that will cause an accumulation of negative charge here. And an accumulation of positive charge here. So you can think of that like a sigma also. This becomes like a capacitor or a total charge Q also. So there is plus Q and minus Q. Now this plus Q and minus Q are going to be instantaneous. We'll discuss why. So that creates an equal and opposite electrostatic force like this, which is going to be E into the internal electric field. Okay, the internal electric field will point along actually the negative x-axis, minus E. That's why the electron is experiencing a force along the positive x-axis. So this is your concept of induction. Right? This is like this is actually this thing, your motion generated EMF. That concept DLP hota hai na वैसा. So the potential difference will be that electric field into D, and that electric field will be how much? B into B. So we are just rederiving that also. Okay? So because your magnitude of magnetic force is equal to your magnitude of electrostatic force on any free electron. So we are doing this analysis on a free electron. Okay, so this is, I mean, you don't even need to do this calculation. I'm just showing it to you separately, but you know the result. It is BLV. So यहाँ पे वो L क्या होगा? इसका thickness होगा disk. So magnetic force is EBV in magnitude. That has to be balanced by your internal electrostatic force, and this is an electrostatic field because there's actual static charge. And it is not that second type of electric field which happens in time varying magnetic field. where it is a non-conservative field. This is actually a conservative electric field. So this is your field. So in fact, this thing is like this. It is along minus I cap. So therefore, there will be a potential difference, delta V, okay, which you can say is equal to magnitude-wise, it is E into B. So that is BVB. Okay. So in fact, coming back to this diagram here, if I take this surface as surface A and this surface as surface B, you'll see in terms of potential difference, this delta V, surface A is at higher potential, surface B is at lower potential, and that is equal to BVB. Is directly proportional to V. But understood this so far? Okay. So next thing
Yes,
is
sir.
how much. So that is your potential difference. Okay. Now the next thing is we have to understand how much is this electric field in terms of charge. Okay. So electric field, which was basically V into B, is also equal to what? Sigma upon epsilon naught. Just use Gauss's law over here. So if you take a Gaussian cylinder inside this metallic sheet kind of thing, so very interestingly, यहाँ पे क्या हो रहा है? The metal is not in steady state. So that is why there is going to be electric field inside the metal. And normally what we say for a metal, there is no electric field inside it. But here that is not going to be the case. Here there is going to be electric field inside, whereas outside the electric field will be zero. Because the effect of this charge and this charge are cancelling each other. So inside, the effect of charge is going to be electric field like this. And that electric field, whether you use Gauss's law or whatever you use, you can show that it will be sigma upon epsilon naught. Because each layer of charge is creating sigma by 2. So sigma by 2 plus sigma by 2, so that electric field is Q upon epsilon naught into pi r square. And that is equal to what? V into B. Now connecting it with the above equation. So you have a relationship in the above equation here. Somewhere here I must have written. This one. So you have this relationship.
Sir,
Which is giving you the
electric
relationship
field.
between.
Sir,
So
sir,
ये electric field किसकी वजह से? Tell me बेटा.
sir, electric field अंदर zero क्यों नहीं होगा?
Because यहाँ पे क्या हो रहा है ना, the conductor is always in a state of flux. The electrons, inside the conductor, they are experiencing magnetic field, and that magnetic field is that magnetic force is increasing with time because we are assuming it's accelerating.
Okay.
So because V is increasing, so the magnetic force is increasing all the time. So to counter that increasing magnetic force, I have to have an increasing value of electrostatic force. So that means the charge accumulation on either side has to keep increasing. And in any case, see what happens in a moving conductor inside a magnetic field, there is electric field. It is only when there is no magnetic field, at that point of time, the electric field is zero. So in electrostatics, when we discussed in conductors that in steady state, the electric field inside the conductor is zero, that is because there was no magnetic field. Or even if there was magnetic field, the conductor was stationary. But the moment you start moving the conductor, because of this accumulation of charge, which is trying to cancel the effect of magnetic field now, there is electric field inside the conductor. That is why there is potential difference across the conductor. So potential difference BLV आता है, that is showing you that there is electric field inside the conductor. So anyway, so coming back to this, in terms of the instantaneous charge, this is the relation of electric field on the surface. And in terms of the magnetic field's effect, this is the relationship. So now connecting these two relationships, you can see the relationship between immediate amount of charge, which is Q. So the electric field is Q upon epsilon naught pi r square. That should be exactly equal to what? It should be equal to V into D. So that shows you the instantaneous charge on each surface is like that. It is epsilon naught pi r square into the uniform magnetic field into the velocity V, which is why I'm writing it like this, because the velocity V is variable, that is making Q variable. Whereas everything else in my bracket is constant. So you got this relation now that the amount of charge is directly proportional to the amount of velocity. Okay. So this is, I think, the first part of the question. Let me go back to the question and see once. So yeah, the amount of charge induced on the surface at an instant when the shuttle speed is V. So this is what you have to do. Okay. So the amount of charge induced is going to be like this. All right. Now coming back to this, now I'm going to scroll down to the second part of the question. So now read the second part of the question. Now it says magnetic force acting on the shuttle during its fall in terms of the shuttle acceleration. I have to find the magnetic force. So now this becomes interesting. Okay.
Sir, we differentiate the equation.
हाँ वैसे कर सकते हैं. So what is happening? ये जो charge है, इसका एक rate of change है, and that is like a horizontal current that is happening. So if you think of the whole metallic disc like you said as a conductor from the side.
सर इसमें मैग्नेटिक फ्लक्स चेंज हो रहा है ना?
नहीं.
Magnetic flux नहीं change हो रहा है. Because see the magnetic field is uniform, na? So magnetic flux is not changing. Okay, but there is motion inside a uniform magnetic field, and that is creating motion generated EMF. You understanding? So it is something like this, that inside a magnetic field like this, if you take a rod, like you take a metallic rod and you start moving it with a velocity like this. Now what is happening? There is no closed loop, no? It's just a single rod. So there's no question of flux here actually. So like that also, if you consider a disc, now instead of a rod, this whole thing is a disc. So there was no flux to begin with, you know, because magnetic field lines कैसे थे? वो disc के surface पे tangential थे. They are not cutting through the surface. So there's no flux to begin with. But the motion is going to generate a potential. Here, for example, B cross B points like this. So this is going to act like a EMF like this. It's going to act like a EMF of B. So that is what is happening to the whole shape over here instead of just a single rod. Okay. So
सर लेकिन वो जो इलेक्ट्रिक फील्ड उसमें जो जनरेट हो रहा है उसका पर्पस क्या है? मीन मतलब क्या बैलेंस कर?
I'll explain to you. Okay, क्या purpose है देखो. See, I wanted to find out the relation between charge and velocity. You know, that is where my electric field concept came in. Because the electric field gets induced according to the amount of velocity. That's what my first equation is telling me over here. That as the velocity is increasing, you know, the electric field is increasing. And the electric field is increasing. Now, what is creating the electric field in the first place? Accumulation of charge. So, मेरे free electrons क्या कर रहे हैं? Migrate कर रहे हैं towards the left, which is leaving behind a positive charge on the right. So, ये जो process of migration है, had the velocity been constant, ये process of migration एक fixed हो जाता. They would have, I'd have had a fixed amount of charge minus Q and plus Q, which would give me a constant amount of electric field where this equation is balanced. But now what is happening here? This velocity is increasing with time. So accordingly, what electric field is increasing with time. So accordingly, what is happening? My charge that is increasing with time. So
Okay,
charge,
sir, got it.
So if charge is increasing with time, that means there's an equivalent current in this direction. Inside the conductor, along the there is an equivalent current which is flowing, and that current is basically what it is: dq by dt. Now just differentiate this relation that we got. So differentiate that relation, so that equivalent current is becoming epsilon naught pi r square into b into the acceleration, because you're differentiating that. Okay. Now this current is flowing through a distance of how much? Through a distance of d. So a current element like this of distance d, it will experience an ideal element will experience in a magnetic field coming out like this, ideal cross B. You can see the direction of magnetic force will be like this, and always it is in agreement with Lenz's law. So on a small current element, the magnetic force would be ideal into B. So on the summation of all the current elements which are between the two surfaces, so if you sum up all these current elements ideal, you get the net magnetic force, which is IB into summation of dl over all of them. So that is becoming nothing but small d. So your magnetic force is becoming this current, which we had written here, epsilon naught pi r square into b into this thing, okay, into b. Okay, so this is just a current. So IB into this integration of dl, which is d. So that is what it will tell you, that your magnetic force at any instant as a function of the instantaneous acceleration is like this. It is epsilon naught pi r square b square, correct, into d into the linear acceleration. So this is what the answer to the second part should be. Okay. So I will share the whiteboard with you guys, so you don't need to worry about writing down every detail and all that, or taking screenshots and all. But just make sure you understood. So I'm just minimizing and showing you the calculation of this. Right, guys. So hope this is clear up to this point.
Yes, sir.
Now we'll just take a quick 2-minute recess, because other than anything else, my white screen has again frozen. Okay, so I need to reboot that one. So just take a quick 2-minute recess and absorb this question. I'll just be back. these are the and you see the ones here, these are the internal forces. Okay. So that is why my horizontal momentum is conserved, because the external force doesn't have a horizontal component. Okay. So now let us get back to horizontal momentum conservation as an equation. So as far as the person is concerned, or let's start with the wedge. Okay, so the wedge will have at this point of time a horizontal velocity in this sort of direction. So let us say this is the velocity of the wedge with respect to ground. So this is VW. This is the velocity for the wedge, capital M, with respect to ground frame. So let's come down to the momenta, analysis of the momenta. So my capital M is having a momentum which is like this. So the momentum of the wedge is just mvw I cap. But now let's talk about the particle. So talking about the particle or the person, what about his momentum? Okay. So in that diagram, this was his relative velocity, and it would have been in the tangential direction. So in this diagram, you can see this velocity v0, which is his relative velocity, is along the tangent. So if from this point, suppose he's at an angular position theta like this over here, then this at an angle theta to the vertical like this. So with respect to the starting position, which was here, if he's made an angular displacement of theta, then in this diagram here, this v relative is at an angle theta like this. So the relative velocity of the person with respect to the wedge, so that I can write as v of small m with respect to the wedge, that is equal to v0, because this magnitude I have taken as v, which is a constant. This term. v0 into sine theta, angular displacement of the person from a starting point. So theta is not his angular position with the vertical, it is the angular position with the horizontal. Whereas the velocity of the wedge itself, we just saw, is some VW, which I don't know, but I can. So in the ground frame, what is the velocity of the person becoming? This is with respect to ground. That will become the relative velocity plus VW. So this should become V0 sine theta plus VW I cap plus V0 cos theta. So now I've got these two terms. I've got the momentum of the wedge and I've got the momentum, but there's a problem in this. I'll just explain what this is right now. Momentum of the man is m into this term. V0 sine theta plus VW I cap plus V0 cos theta. Now what should happen? The system's horizontal momentum should be 0. So the vector sum of these two momenta should be such that it's only pointing vertically. Okay. Now tell me what the problem here is with this. If you want to make the system's horizontal momentum 0, Just a second. You want to make the system's horizontal component of velocity 0. What was the problem in that equation? I'm coming back to that. Okay. The problem in that equation is that the way I wrote it, the person small m also had a positive x component of momentum, and the wedge also had a positive x component of momentum. So how can that be 0? Okay, so that is the problem that we are coming across. So what is ultimately the solution to this? That's what we have to understand next. Okay. What is the solution to this? So has anybody figured out what the problem is? Wait, my OneNote is just misbehaving while I'm restarting that program. Just hope all of you understood what the issue was I was telling you about. The issue is that the way I have written my equation, system का horizontal momentum 0 हो ही नहीं सकता है. You understanding why it can't be 0? Because both the person's horizontal momentum as well as the wedge's horizontal momentum, they were both along the positive x direction. So how can their sum be 0? So the thing is, okay, so for whatever reason I have lost that page, but I'll explain to you. The thing is that there was something wrong in my impulse diagram, and therefore there was something wrong in my analysis of forces. I mean analysis of momentum, and I'll show you why what was wrong. Okay. So I'm guessing, I'm hoping that some of you figured this out. क्या होगा कि दोनों का horizontal component एक direction में नहीं हो सकता. One has to be positive, the other has to be negative. Okay. Now that means actually what is happening? The wedge is not going forward at this point of time. The wedge is actually coming backwards. But then that makes you think कि अच्छा wedge अगर backwards आ रहा है, उसको impulse कहाँ से मिल रहा है? Because the normal impulse of the person seems to be pushing him that way. But remember one thing, that the person is climbing up on a surface without decelerating. He's climbing up like this at uniform speed. So his tangential acceleration is 0. So something must be countering his empty sine theta component. So there's also friction involved. So when you see the mutual forces between the wedge and the person, it is not just the normal contact. On the person, there is friction acting tangentially and there is normal impulse acting tangentially. So these are the forces that the wedge is applying on the person. There is normal reaction and there is friction. So coming back to the wedge, at that point on the wedge, what are the forces acting? The forces acting are opposite. Normal reaction is into the plane, and this thing is down inclined. So on the wedge, standing, the person will be applying a force on the wedge such that he is pushing the wedge backwards, with the friction on his feet, and he is pushing it into the plane with the normal reaction that is this thing is applying. That is, so this is the friction and the normal reaction on the wedge due to the person. And in addition to that, of course, there are the external forces which are ng and normal. So this is the complete
Sir,
force
will the work done by this normal?
That will be.
Sir, can I speak?
Yeah. The work done by the normal.
So the work done by the normal on the system will be 0 or
the work done by which normal? The mutual one or the one from the floor?
the mutual one?
So see, the mutual one, what is happening is that his foot is in contact with the ground now. So the point of contact on the wedge is having the
Yes.
displacement as the point of contact on his foot. Okay.
Yes,
Whereas
sir.
these two directions are equal and opposite. So in a small time dt, ठीक है, अगर जो उनका उसका foot का और wedge का point of contact है, उसका displacement ds है. So this normal reaction is doing n dot ds. The other one is doing minus n dot ds.
Okay.
So the resultant is becoming 0. Same for friction.
Yes, sir. Fine.
And that's why those forces are ending up not doing any work. That's also very important to understand over here. Okay. So
Okay, sir.
just to make this diagram a bit clear. Okay, so if you just combine these two diagrams, you will get the total picture of forces. I have not drawn them in the same place, but you can see these are all the forces which are on the system. So in this, the black colored forces, they are the external forces, and the red one will force. And the black ones, they are the external forces. Provided, of course, we are considering the system. We're taking the system as the person, small m, plus the wedge, capital M. Okay. And as we discussed earlier, we can only apply conservation of horizontal momentum to the system. This has to be 0. So very interestingly, you can see this friction का जो horizontal component है. Now come to the free body diagram of the wedge. So on the FBD of the wedge, the friction is giving back horizontal impulse. The normal reaction is giving a forward horizontal impulse. But which one is dominating? It is the friction. So ultimately, in terms of motion, what will be happening is very interesting. In terms of motion, this is what will be that while the wedge will be having, or while the person is going up the incline, the wedge will actually be coming back. It's counterintuitive because you always feel he's pushing it like this, but you remember he's pushing it backwards by friction. So at this point of time, the wedge will be having a velocity like this. This is with respect to ground. Okay. Whereas the person, his velocity, the tangential one, v0, this is the relative one. This is relative to the wedge. This. So this is our momentum picture. So now let us convert this momentum picture into equation and understand what to do. So hopefully the rest of the question will be clear from this point onwards. Okay. So I mean, see, to solve the problem, you don't need the impulse picture. You just need to apply momentum conservation in this diagram. The earlier two diagrams are not necessary at all because I'm not doing any force analysis. I'm not applying Newton's laws anymore. But it just helps you understand why the direction of horizontal momentum of the wedge is in fact backwards. It is not forward. Okay, so okay, so people, unfortunately, my OneNote is, my whiteboard is once again misbehaving. So I will switch to another whiteboard. Switch to, let me see if this one whiteboard looks nice. Okay. So now coming to the momentum picture, this is having a momentum backwards like this. Okay. So VW, okay, and this mass is M, whereas the person is having a momentum which will be the vector sum of this V0 and this VW, because this is relative. Okay. So again, in that diagram, if I had assumed that we had climbed to an angle theta, so then this angle would be theta. So the velocity of the person with respect to ground will actually become V0 sine theta I cap plus something into J cap.
सर ने क्या एग्जिट कर दिया?
Yeah, people. So sorry about. I got disconnected from the internet. So hope you guys are getting my audio now. So I'll just share the final equation of that one with you before we move on. Okay, people. So I'm having a little bit of trouble with my internet route. I'm just showing you the solution of this one. This moment,
So
just take
your
a note
voice
of
is
this and try to
lagging.
complete this problem. And in the meantime, I'll just have to reboot it. I'll and get back to you. Yeah, people. Unfortunately, yeah, people. Unfortunately, my internet connection is down, so I'm just rebooting my router. Right now, I'm talking to you through my 4G phone, so probably you will not be getting good images and all. Just take a 5-minute break after you complete that screen share. Okay, that problem from horizontal momentum conservation, the final equation I've written. Just try to work that out and complete the problem, and take a 5-minute break. I'll be back online. Okay. Thanks, guys.